So problem 1 from exam number 3 should look familiar to you, at least part A, because this was a homework problem from a recent assignment. The problem says that you hang two balls from strings of identical length L. One of the balls hanging vertically and at rest initially has a mass 2m, and you pull the other one, which would just touch this one if it was also hanging at rest. It has a mass m, but you pull it aside, okay, and also has a length L for the string. You pull this mass m aside to a height h, then release it. It falls down and collides with the block or the ball of mass 2m. And the homework, you were asked to analyze a subsequent motion in some detail. How high do both masses bounce after the first collision? Then they fall down again and collide a second time. And you're asked how far they bounce after that second collision. But this is an exam, so I went to shorten it and just to see if you understood how to handle the initial collision. Okay. Now, you can't solve that entire problem in one fell swoop. You have to break it into two parts. The motion of this ball down until just before the collision, that process is controlled or can be analyzed with conservation of energy, because we'll take gravity into account with its potential energy. So there are no forces, frictional type forces, and so we can say energy is conserved, the same before and after. And then we'll move on from that to analyze the collision. But let's go ahead and do the first part first. So I'll define U gravity equals 0 at the low point, just to be clear. Okay, so this is the place where U gravity is defined to be 0. Okay, and you're told you pulled this ball over to a height h, and so we'll just use the idea that the final energy, now final in this case is just before the collision and just of this mass m, but its final energy equals its initial energy. Its final energy, well, it's down here where gravity is 0, so its final energy is all kinetic. Call that 1/2 mv, and I'll use a subscript L for the left ball and not, because this will be the velocity after it falls this distance, but just before, or the original velocity just before the collision, squared. That equals the original energy. Well, there's no kinetic energy there. You pull it aside and it's at rest when you release it. So this is all gravitational potential energy, or just mgh. Okay, and what we can get from this expression is VL naught equals, just do the math, the m's cancel out, multiply both sides by 2 and take the square root to get VL naught, the square root of 2gh, which you should think is familiar because you've seen it pretty often already this semester. If you just drop a ball from a height h, this is the velocity it will have after it falls that height h. And nothing is different about letting it fall down attached to a string compared to just dropping at the same velocity, although in a different direction, horizontal instead of vertical. Okay, now we can analyze the collision because we know the original velocity of the left ball before the collision. The other ball, the right ball, or the 2m ball, is at rest. Okay, so let me just write that down. VR naught equals 0. So the problem tells you that you don't have to analyze this from what I would call first principles from conservation laws. You may use information from the formula sheet. And you were warned about this in class. I've given you the formula for the elastic collision, the final velocity of the two balls in terms of the initial velocities of 1 and 2. This is 1 striking 2. And in this case, V2 naught is going to be 0, so we can ignore this term and this term. So things are a little bit simpler than they could be. So let me just write down those general formula to make life easy. So V1 final, this is just from the formula sheet, equals V1 naught times M1 minus M2 divided by M1 plus M2. And V2 final equals V1 naught times 2M1 divided by M1 plus M2. So that's a very general collision with M1 moving with a velocity V1 naught and M2 moving with a velocity V2 naught. That's how we arrange things in class. Now we have to apply this to our specific situation, and we know the V1 naught well, V2 naught is 0. We know V1 naught is actually V left naught in this case, and M1 is M. M2 is 2 times little m. So I'll just write down the answers basically for our problem. V left final, which is V1 final, is equal to V1 naught, which is the square root of 2GH from up here, times M1 plus, or M1 minus M2, well that's M minus 2M, divided by M1 plus M2, which is M1 plus 2M. Sorry, there's no 1 there. Okay, and hopefully you can do this math. 1 minus 2 is minus 1 divided by 3. So our answer is minus 1/3 square root of 2GH. And the problem also asks you to describe carefully the direction of the motion of each ball afterwards. The negative sign here, since in this formula we're assuming positive is to the right for everything, so this negative sign just tells us that the motion is to the left. In other words, this ball comes down, hits 2m, and bounces back towards the left. Similarly, we can write down the final velocity of the right ball of mass 2m using this expression. Translate it into our terms. V1 naught is again, let's see, this will be V2 final. V1 naught is still square root of 2GH. Now we have 2m1, or 2m, divided by m1, which is m, plus m2, which is 2m. So this is just 2/3. So our answer here is just 2/3 square root of 2GH. And that's positive, so that's to the right. And so those are the answers to part A of this problem. Part B says if you didn't have access to the formula sheet and had to get this result from scratch, how would you go about that without doing the algebra? Because I don't want you to take time on the exam to work out a lot of algebra. So here all you had to do is write down the two equations, one for conservation of momentum, which is just P naught equals P final, or, okay, P naught is M V naught L, only momentum is in the ball of mass M, not 2M, moving with its original velocity just before the collision. After the collision, you have both balls moving, okay, so we have then plus, well, this equals to M V final L. Now notice I'm just writing M V final L, but V final L will be a negative number. Okay, we found that up here, but I don't have to put that in explicitly because that'll come in when we plug in for V final, plus the momentum of the other ball, which is a mass 2m, okay, and it has a velocity VFR. And that's the conservation of momentum equation that you're asked for. Conservation of energy equation. Okay, just says that the initial, or the initial energy equals final energy. Now we're just talking about initial just before the collision and final just after the collision. And these are equal because you're told it's an elastic collision. Okay, so if we write this down, we've got 1/2 m v naught L squared. Okay, that's the initial energy. It's all in the left ball of mass m and velocity v naught L squared equals the kinetic energy of that same ball after the collision. So that'll be V, well, it should probably written, yeah, it should probably written as L naught to be consistent with what I'm doing up here. 1/2 mv L final squared plus the kinetic energy of the 2m ball, which is 1/2 times 2m, and you can cancel out these half and the 2 if you want, times V final, or V right final squared. And those are the two equations you were asked to write. If I hadn't given you the formula from the formula sheet that we used to get this, you would then have to do the algebra to convert these two expressions into these forms, but didn't have to do that for this exam. That just leaves us with part C. Part C says, this collision isn't elastic, it's completely inelastic, which means the two balls stick together after the collision, and you're then asked what would be the speed that they're moving at. Remember, there's just one speed because they're moving together. Well, in any collision, we know that P final equals P naught. Energy is not conserved if it's completely elastic, but this is still true, and that's all we'll need, because this tells us that the final momentum is just 3m v final. There's no left or right here. There's just one velocity for the combined pair of balls of mass 3m. That equals to the initial momentum, which is mv naught L, all in the left ball because the right one's at rest, or m times the square root of 2gh, because we really shouldn't write an answer in terms of v naught L. So we can solve this expression pretty quickly for v final. Just divide everything by 3m, the m's cancel, and we have 1/3 square root of 2gh, and we're done with problem 1.